Good afternoon, students. It's already time for the class. We'll wait for 5 more minutes. There are many students who are trying to join this meeting. I'll keep admitting them. We'll start at 5:03. We'll wait for 5 more minutes. Till then, those who have joined, uh, if you are if you have attended previous practice problem sessions, you should know to keep on your mic muted and turn off your video chat. This will be an interactive session, and any interaction with me will be through the chat box. So we'll try to solve practice problem related to lecture week 5. And I request again everybody to please turn off their mic and switch off their video chat. Any interaction will be, with me will be via the comment box. So I'll keep admitting students and we'll start at 3:05. It's already 3:05, and there will be participants still coming. Let's not waste any time and start this session. So today we are going to solve, as I said earlier, practice problem set week 5. So all of you must have received the week 5 lecture sections for this course, Nanotech and in Agriculture. And my name is Ashutosh Behera. I'm a PMRF scholar, PhD from IIT Kanpur. So we'll be going through this practice problem session very soon. First I'll do is I'll share my screen, and again as I've mentioned in the chat box, any communication with me through will be through the chat box. Participants are required to mute their mics and turn off their video chats for smooth conduction of this session. So let me share my screen with you all. And I'll just share my slides here. For all of your information, these sessions are recorded sessions. So you will find all these practice session recordings on my YouTube channel, and the link must be provided from NPTEL. If you check your earlier emails, you must have the link for the slides. So I'll share these slides, and the recordings for this session will also be available. You can visit the YouTube channel and rewatch it if you have missed it. So I'll just present my screen, and if you can see my slides changing and my voice is clear enough, audible, is it audible, students? You can just type yes or no in the chat box and let me know. Can you see my slides changing, and is my audio clear enough? Then we can start this session. And to all the new joinees, we will be doing practice assignment for week 5 lecture set, and all the students please mute their mics and turn off their video chat. Meanwhile, I'll keep admitting students who are requesting to join this call. So with that, let me start today's session. Let me switch on my laser pointer. Yeah. So the course that we have all enrolled for is NPTEL Nanotechnology in Agriculture. We are going to solve practice assignment week 5. The instructor is Professor Mainak Das from IIT Kanpur. And as I have mentioned earlier, I'll be the TA for this course. My name is Ashutosh Behra, and I'm a PhD PMRF scholar from IIT Kanpur. So all this practice assignment will consist of 10 multi-choice questions, the same that you get in your assignments, and we'll solve them together one by one and solve the rationale behind the correct answer. Right? I will ask students to guess or to answer the question, wait for them, collect some answers, and then show you my slides regarding the rationale behind the correct answer. This is how the assignment proceeds, right? So the first question for this practice problem set is: in which of the following compounds iron exists in a higher oxidized form? This is the question, students. In which of the following compounds iron exists in a higher oxidized form? Option A, FeS2. Option B, Fes. Option C, Fe2O3. Option D, none of the above. So the question is in front of you. There are 4 options. Students, please try to answer. What do you think is the right answer? You can mention in the chat box. You can either type the answer or you can just mention the option which you think is correct. I'll wait for 5 minutes and collect some answers before we'll proceed into knowing which is the correct answer. Meanwhile, all the new joinees, please mute your mics and turn off your video chats. All communication with me will be via the chat box for the smoother conduction of this session. And we are going through practice problem set 5 corresponding to lectures of week 5. And this is the first question that we have come across. In which of the following compounds iron exists in a higher oxidized form? Yeah, all the students again, please mute your mic and turn off your video chat. I got your answer. There are many answers in the comment section. You can just type your answer in the chat box. So please refrain from using your mic and video chat. Many people have answered option 3C, and the correct answer is option C, Fe2O3. So you guys have answered correctly. Now, what is oxidation number of a compound? So the number of electrons an atom can donate or accept to form a bond with another atom is the oxidation number of the oxidation number of the element. So the number of electrons which it can donate or accept for a bond formation. And oxidation number determination has some set of rules that all elemental states have zero oxidation number. The definition says oxidation number, also called oxidation state, which was the question. Total number of electrons atom either gains or loses to form a bond with another atom. The sum of each element oxidation number needs to total the charge on the compound, and oxidation number is often equal to the charge on the element unless bound to a more electronegative element. So this is just a rule stating that the sum of each element in an element oxidation number. Suppose if you take for an example KMnO4, so K is oxidation number, potassium is +1, Mn is +7, and O is -2, and there are four atoms of O. So the total charge on the molecule is 0 because this is an uncharged species. Sum of each element oxidation number needs to total the charge on the compound, and oxidation number is often equal to charge on the element. So here the compound charge is 0 and we have potassium +1, manganese +7, and oxygen -2. So that's how the oxidation number is calculated. And the oxidation number is often equal to the charge on the element. Whatever charge the element carries is most of the times the oxidation number. So if we look at the three compounds that we have in our options, FeS2, if we break down FeS2 or if we dissolve it in water, these are the ions FeS2 is going to produce. It is going to produce two S minus ions and one Fe2 plus ions. So here the oxidation number of iron is 2 plus. The next compound FeS, if you dissolve it in water, then there will be two group of ions, Fe2 plus and S2 minus. So here we will get iron with oxidation state again 2 plus. While in Fe2O3, if you dissolve this in water, the ionic states will be O2 minus, 3 molecules of O2 minus and 2 molecules of Fe3 plus. So Fe2O3 we can recover Fe3 plus iron species. Fe3 plus therefore is the highest oxidation number, highest oxidation state of iron, which was the correct answer. Right? Is it understandable, students? Did you get it? Is it clear? You can just mention yes or no, and we can move on to the next question. Is it clear to the students? So I've just discussed how to calculate an oxidation number, and you just have to dissolve whatever compound you have in water and see what kind of ions or charge uh, you get on an element, and that in most cases will be the oxidation number of the element. Cool, cool. Yeah. Moving on to the next question. Question number 2. If a larger particle size solid is not at all soluble in water, example, sand in water, the mixture is called dashed. So if you read the question carefully, a larger particle size solid is not soluble in water, then that kind of mixture is called A, solution, B, colloid, C, suspension, D, none of the above. Let me know in the chat box what do you think is the correct answer. A solid is not a solid is having larger particle size and is not soluble in water. Then what kind of solution will that be? I'll wait for a minute to collect some answers. You can type your answers in the chat box. Yeah, I see some answers. Aditi says 3, Roshan 3, Anjali Sharma 3, Avinash is saying 1, Komal 2, Ganeshan says 3, Kirti suspension, suspension. Okay, so there are wide variety of answers, but most of the students are going for suspension. Some think it's a solution or a colloid. Let's see what is the correct answer. So C, suspension is the correct answer, as many of you have answered correctly. Very good. So let's see what is a solution, a colloid, and what is a suspension to clear the confusion between all the three states of solution. So a solution is a special type of homogeneous mixture composed of two or more substances. So solution is a homogeneous mixture. It means both the components will be dissolved and you cannot separate it physically. You cannot separate one component physically from the other component. That is a solution, which in our case is not an answer because it is given in the question sand is not at all soluble in water. So a mixture of sand in water is not a homogeneous solution because you can isolate sand physically from a homogeneous from the solution of sand and water. So it cannot be a solution. Solution is a homogeneous mixture. And in such a mixture, in a solution, a solute is a substance dissolved in another substance known as a solvent. So this is a common terminology saying solvent is the substance in which another substance called solute is dissolved. So a solution has two components, a solute and a solvent, and it is a homogeneous mixture of those two components. Whereas a suspension is defined as a heterogeneous mixture in which solid particles are spread throughout the liquid without dissolving in it. So this is the right answer for C, option C. Suspension is a heterogeneous mixture where you can physically separate one of the two components. Like here we can separate the sand particles from the sand water solution, and in a suspension solid particles are spread throughout the liquid without dissolving in it. It's not dissolving. So this is a schematic diagram showing this is a solution which is totally homogeneous. both of the components lose their individual identity and you cannot separate them physically. While this is a suspension in which the blue dots that we see is the solid particle. There are also some solid particles which are sedimented in the bottom of the tube, and this gray liquid is the fluid or the solvent. So solid particles haven't completely dissolved in the liquid and some are precipitating. So if you run this tube in a centrifuge, what we will see is a picture like this, where we'll have a supernet or the supernatant of the solution containing the liquid part of the solution and precipitate part accumulating all the undissolved solid particles. So this is what we get when we centrifuge a suspension. But when we centrifuge a solution, we would not get any separation because any physical method would not give us the separation. Right? So this is a difference, basic difference between solution and a suspension. Solution is a homogeneous mixture and a suspension is a heterogeneous mixture where particles do not dissolve in the solvent. And an example of a suspension would be sand in water, which was the question. Sand in water is a suspension. The suspended particles are visible under a microscope and will settle over time if left undisturbed. So that's the same thing here. The blue precipitate that we see, if we allow the suspension of sand in water to stand down or to just settle, keep it untouched, then it will settle down. The sand particles will settle down at the bottom of the tube forming a sediment. So that is an example of suspension. Now what is a colloid? A colloid is a mixture in which one substance consisting of microscopically dispersed insoluble particles is suspended throughout another substance. So here the definition says there is a substance which is insoluble and is suspended throughout another substance. So it's present everywhere in the substance or in the solvent, but it doesn't dissolve because it's insoluble in the solvent. And we have many examples of colloids from our day-to-day life. Jellies, whipped cream, milk, even mist are colloids. Because they coexist, they do not sediment or they do not settle down, but they are also consisting of insoluble solute particles through another substance. So in jelly we have insoluble solid particles in a gelatin kind of a mix. In whipped cream, in milk we have proteins as microscopically dispersed insoluble particles, casein protein for milk in a suspension of water. That's how it forms a colloidal solution of milk. So these are basic differences between a solution which is homogeneous, a suspension which can sediment down the and physically separate the particles, a colloid in which insoluble particles is suspended throughout another substance. So our answer to the question mixture of sand in water will be a suspension. Is it clear to the students? Let me know in the chat box if it's easy to understand, if it's clear. Great, great, nice. So again, I would like to inform the new joinees. Please turn off your mic and video chat. And any communication with me will be via the chat box. We are here solving these questions simultaneously. And if you think you know the right answer, you can type in the comment box. I would encourage all the participants to participate in this session so that you can make the most out of this practice problem session. So this is the kind of revision of what the course structure has followed. So the live lectures are of week 7 are out, but we are solving an assignment related to week 5, so that it's kind of a revision before your exam comes and you brush through your topics again. So I would request all of the participants to maximally participate and answer these questions. Let's move on to the third question.
Galacturonic acid is main component of dashed. Galacturonic acid. Option A, proteins. B, pectin. C, lecithin. And D, amino acid. I would encourage all of the students to try to answer. Even if you guess it, it's wrong. Do not feel shy. Be confident. We will come to what is the right answer and understand the rationale behind why the right answer is the correct answer. Right? So I encourage all the students to participate. All you have to do is type the option that you think is correct for this question in the chat box. Galacturonic acid is main component of A, proteins. B, pectin. C, lecithin. D, amino acid. I'll wait for a minute or two and collect some answers in the chat box. Then we'll proceed. Okay, so there are answers, some answers. Aditi says 3, lecithin. Roshan says 3. Gaurav says pectin. Kirti is also going with pectin. Vinay says 3. Anjali 2. Avinav B. Rupa Devi says B. Shurbi Thakur said D.
Okay, okay. So there are wide variety of answers, but I see majority going with pectin and lecithin, right? So let's see what is the correct answer.
The correct answer is B, pectin. So all those who have answered B, congratulations, you are correct. Galacturonic acid is the main component of pectin. Now what is galacturonic acid? D-galacturonic acid is a sugar acid, an oxidized form of D-galactose. So galacturonic acid is an acid of galactose. Galactose is a sugar molecule, and when we have COOH to that galactose, we get galacturonic acid because COOH is the carboxylic acid group. And D-galacturonic acid is the main component of pectin, which was the question about, in which it exists as the polymer of polygalacturonic acid. So pectin is nothing but many molecules of galacturonic acid joined together to form a polymer which is now known as pectin. In its open form, so now we are talking about one galacturonic acid unit. In its open form, it has an aldehyde group at C1 and a carboxylic acid group at C6. So this is the structure of D-galacturonic acid. So if you see, there are many functional groups here. So this group CO2H here is the acid carboxylic acid group COOH, and this is the structure of galactose. So to a galactose, we have just added a carboxylic acid group, which makes it galacturonic acid. And this is the functional unit, repetitive unit of the polymer, which is many such molecules of galacturonic acid join together to form pectin. So in its open form, it has an aldehyde group at C1 and carboxylic acid group at C6. So this is the C6, and in open form, this O will be an aldehyde group. That's what it is saying. And galacturonic acid is an acidifying agent in foods and the monomer of protein molecules. So in commercial world, Galacturonic acid is used as an acidifying agent in foods. So if you want acid in your food, if you want your food to be sour, because acid presence of acid makes food sour, and if you want emulsification, so many processes, galacturonic acid is used as an acidifying agent. Now, what is pectin? Pectin is the principal component of middle lamella where it binds cells. So if you look at plant or animal cells, so there are certain layers called middle lamella or junctions between the cells. One cell binds to the other cell or to the ground membrane or to the matrix with the help of middle lamella, which is consisted of pectin. Pectin is also deposited by exocytosis into the cell wall via vesicles produced in the Golgi apparatus. So where does this pectin come from? Pectin comes from Golgi apparatus. The Golgi apparatus is the cellular organelle in which all the protein sorting, molecule sorting is happening. So the Golgi apparatus channels these pectin vesicles into the cell wall, and via a process called exocytosis, this pectin is deposited into the cell wall, forming the middle lamella. So it's a hard structure, it's a hard and thick structure. The amount, structure, and chemical composition of pectin is different among plants, within a plant, over time, and in various parts of plant. So the amount, structure, and chemical composition, that just means to say pectin is so variable. It changes from plant species to plant species. Plant over time, younger plants and older plants may have different levels of pectin, and various parts of plant will also have different level of pectin. So pectin is a molecule which provides rigidity to cells of a plant. So whichever organ or whichever stage we need rigidity and we need hard force, we need pectin. So those areas, pectin will be high inside plant. Pectin is an important cell wall polysaccharide that allows primary cell wall extension and plant growth. So it's an important polysaccharide, and this is how pectin molecule looks like. So this single unit is what we understood in the previous slide, which is galacturonic acid. There are multiple such galacturonic acids, and there are many modifications. So if you see here, these are some other sugars which have provided identity to the type of pectin present in the plant. And pectin is generally found in plant products such as citrus, apples, and in jams and in jellos. So these are pectin rich foods. So is it clear to the students? Galacturonic acid is the component of pectin. Is it clear to the students? We learned about galacturonic acid. How does it look like? Pectin and its function, where does it occur? And that brings us to the answer to the question that galacturonic acid is associated with pectin polymer. Is it clear to the students? Surbi says yes, Roshan yes, Muttu yes. Yes, yes, cool, cool, cool. Moving on to the next question. Oh, we have something again. Oh, it's the other option compound. There was another option, I forgot to tell you, which people had mistakenly answered. Lecithin. So what is lecithin? So we learnt about pectin, galacturonic acid. And what is lecithin? Let us learn a little bit about that. Let me just move fast. Yeah. So lecithin designate any group of yellow brownish fatty substance occurring in animal and plant tissue which are amphiphilic. So pay attention to this. Lecithin is a fatty kind of molecule or any group of fatty substance occurring in animal and plant tissue which are amphiphilic. Amphiphilic means amphiphilic molecule can both have hydrophobic and hydrophilic phases. So that's what this statement says also. They attract both water and fatty substances. We all know water and fatty oil does not mix. Water and oil form a layer over each other and they do not mix because oil or fatty substances are hydrophobic and water is hydrophilic. But an amphiphilic molecule, amphi means the term has come if you try to understand amphibian. Amphibian is an animal which can both live on land and water. So similarly, an amphiphilic is a molecule which can both be hydrophilic and hydrophobic. So such fatty substances are called lecithins, which are also amphiphilic and are used for smoothening food textures, emulsification, and repelling sticking materials. So these have lot of applications in the industry. And what does lecithins are made up of? Lecithins are mixtures of glycerophospholipids including phosphatidylcholine, phosphatidylethanolamine, phosphatidylainositol, phosphatidylserine, and phosphatidic acid. So all these, if you remember, lecithins are monomeric units of the cell wall, cell membrane. In animal cells and in plant cells, we have such amphiphilic molecules in the form of lipid bilayer. So all these lipids, these are all lipids, phosphatidylcholine, phosphatidylethanolamine, different kinds of lipids which form the cellular membrane or phospholipid bilayer. So lecithins are also made up of those phospholipids and they can be amphiphilic in nature. So here is an example of a lecithin group. The egg yolk containing yellowish browny fatty substance is a lecithin. It can be used for emulsification or smoothing food textures. So many chemicals are extracted from the yolk and used. These are lecithins which are used in industrial manufacturing units. Yeah. Now, so is it clear to the students? Sorry, I forgot about the lecithin part, so I just covered it up. Is it clear to the students? What is a lecithin? What is a pectin? And we learnt about galacturonic acid. I just wanted to see. Yes, yes. Very good, very good. Now moving on to the next question. Which of these species is not generated when iron pyrite is added to water? I'll repeat the question again and students who can see my screen can follow the question. Which of these species is not generated? Not generated when iron pyrite is added to water. Option A H2O2, option B Fe2 plus, option C SO4 2 minus, and option D H minus. These are all different kinds of ions. So the question is if you dissolve iron pyrite in water, which of the ionic species you are not going to get, right? Students, please let me know in the chat box what do you think is the correct answer, and I'll encourage all the students to participate equally so that we make the most out of these sessions, because this is the only live interaction you guys are having from anyone in the NPTEL team from the other course NP Nanotechnology in Agriculture, right? So I would like all of you to answer. It's okay if you answer wrong. Do not feel shy. Be confident about it. Mention in the comment box. You just have to mention which option do you think is the correct option. I'll wait for a minute or two to collect some answers. I can see there are already some answers. I'll wait to 2 more minutes to collect some more answers and then we'll see which is the correct answer. Students, please try to answer. Yeah, I guess people are trying to answer. It's good. Let's look at it. Aditi says option 4. Gaurav, Roshan, Surbi are all with option 4. Komal says hydrogen. Do we have hydrogen? Oh, you meant option 4. Keerti says 1. Anish is also saying 1. Komal has changed either 1 or 3. So I can see why the confusion is arising, because none of these ions are straightforward ions. Only I think Fe2 plus is the straightforward answer to this question. But Fe2 plus is always generated. If you dissolve FeS2, which is iron pyrite, you can get Fe2 plus ions. That is the correct straight answer. So it cannot be option 2. Janish is answering H2O2. Let's see. Let's not waste more time and see what is the correct option. The correct answer is option D or option 4, hydride ion, H minus. This is the correct option. You can get all other ionic species when you dissolve iron pyrite in water. You can get H2O2, Fe2 plus, also SO4 2 minus. We can dissolution of iron pyrite in water can generate sulfate ions, ferrous ions, and hydrogen peroxide also. So here is a schematic showing when you add oxygen and water with FeS2, what kind of species it can generate. It can form Fe2 plus OH2 minus, Fe3 plus O2 minus, Fe3 plus OH minus, and Fe3 plus OOH minus. Also S double bond O. So all these species can be generated. So this O2 minus is the oxide peroxide ion. So in presence of H plus ions, it can form H2O2. So we can get H2O2. OH minus ions, very easy. Fe3 plus, so we can generate Fe2 plus molecules, Fe3 plus molecules, and SO can generate SO4 2 minus. Sulfate ions can be generated from here. So we can generate peroxide ion or peroxide, hydrogen peroxide, due to peroxide generated here. Then we can generate SO4 2 minus from S double bond O. So we just need more oxygen in the presence of water. This will convert into SO4 2 minus, and we can also generate Fe2 plus or 3 plus ions when we dissolve FeS2 in water. So the reaction steps of oxidation mechanism can be separated into two types. Type 1 reactions present lower activation energies and are a redox process that involves oxidation of two Fe2 plus sides on the surface to form predominantly Fe3OH. So this is a type 1 reaction generating OH radicals or OH minus ions and Fe3 plus ions. This species is formed from hydrogen transfer between adsorbed water to the adsorbed oxygen molecule on Fe2 plus side. Then type 2 reactions present higher activation energy and lead to the formation of S double bond O through the hydrogen atom transference from water molecule of to the Fe3OH species forming Fe2OH2. So this will generate OH2 minus radical and Fe2 plus radical. And this is another explanation uh, just to show you these reactions present higher activation energy. So this slide is talking about activation energies difference when you dissolve FeS2 in water in presence of oxygen. The determinant step of this oxidation mechanism involved formation of two adsorbed hydroxide species on the surface. The hydroxide in presence of water form the bulk liquid, react to form two water molecules adsorbed on the surface and the first SO chemical bond. So parallel reactions were investigated explaining experimental detection of O2 minus and OOH species. So these are peroxide and superoxide species. So we can generate H2O2, we can generate sulfate from S double bond O, we can generate Fe3 plus ion. The only ion which we cannot generate is H minus or hydride ion. So this is summarizing the reaction. FeS2 plus 7 by 2 O2 plus H2O. Fe2 plus 2 SO4 2 minus. So here you can see SO4 2 minus is formed, Fe2 plus is formed, and 2 H plus is formed. So it cannot form H minus ions. So H minus or hydride ions is the correct answer. Is it clear to the students? So dissolution of FeS2 in water can produce H2O2, can produce sulfate SO4 2 minus, can also produce Fe2 plus Fe3 plus, but cannot produce H minus or hydride ions. Is it clear to the students? Yes, yes. Cool. Nice. Let's move on to the fifth question. Fifth question is an easy one. Which of the following is a dicot crop? I'll repeat the question again. Which of the following is a dicot crop? Option A, lettuce. Option B, lily. Option C, bamboo. Or is it option D, corn? What do you think will be the right answer? Put it in the chat box so that I can see it. Which of these four crop vegetables is a dicot crop? I'll wait for a minute to collect some answers. You can take your time easily and think. Try to answer even if your answer is wrong. It's nothing to be ashamed of. Maximum participation is always encouraged. Take your time. I'll wait for a minute. Collect some answers. Which of these is a dicot crop? I can see some answers. Anuradha says corn. Gaurav is saying corn. Surbi says D. Aditi is also with D. Anjali, Roshan with 4. Corn. Keith is saying lily. Okay. Komal is saying 1. Abhinav says A. There are some lettuces. There are some corns. So too much varied answer. Lettuce, lily, corn. Nobody is saying bamboo. What if the bamboo is the right answer? Okay, just joking with you. Let us see what is the correct answer. Lettuce A is the correct answer. So lettuce is a dicot crop. Very good, very good. Many people have answered lettuce and they are correct. Lettuce is a dicot crop. So it's just a single answer, memory based question. Not your fault for those who have answered wrong. So to understand why lettuce is a dicot crop, let us first understand what is the difference between a dicot crop and a monocot crop. What is a dicot crop actually? Yes, Komal, you are correct. Lettuce is correct answer. Dicotyledons or dicot, the name where it comes from, is generally referred to the flowering plants or angiosperms in which seeds typically contain two embryonic leaves or cotyledons. So it's pretty simple. Dicot. Dissect the word. Di means two. Cot stands for cotyledon. So any plant when while germinating or in cotyledon state has two cotyledons, it is called a dicot. And examples are all legumes including beans, lentils, peas, peanuts are best example of dicotyledons. And lettuce is also a dicotyledon. So here is the representation of pea plant. If you burst open a pea seed, you will see two cotyledons or two halves of a seed. So these plants are known as dicot. And dicots are generally angiosperms or flowering plants. Whereas monocotyledons, commonly referred to as monocots, are grass and grass-like flowering plants, the seeds of which typically contain only one embryonic leaf or cotyledon. Similarly, you dissect the word monocot. Mono means one, cots stand for cotyledon. So any plant germinating with a one cotyledonous structure is called a monocot. It is also a flowering plant or an angiosperm where the cotyledon is one in number. Monocots include most of the bulbing plants and grains, such as agapanthus, asparagus, bamboo, bananas, corn. So corn, bamboos are all monocots. Daffodils, garlic, ginger, and the list is endless. So all of our major grain plants like wheat grain, rice grain, all come from the family of monocots. Onion are also from monocots. So these we are a bigger consumer of monocots than dicots. Dicots fall under many vegetables, pea, lentils, beans, but the two major crops which are support sustaining the world in green revolution is rice and wheat, and both of them are monocotyledonous. So this is an example, picturesque example of a wheat rye showing a monocot plant. So if you summarize again the difference between a monocot and a dicot, in monocot we have a single cotyledon. For dicot we have two cotyledons. If we look at leaf morphology, we have long narrow leaf and parallel veins in monocot. Have you ever noticed a banana leaf? So the venulation or the pattern of veins is always parallel. So there is a midriff in a banana leaf, and then you have parallel lines perpendicular to the midriff, long and narrow leaf, right? In a coconut tree. While in a dicot we have broad leaf and a network of veins. Just like blood vessels, we have leaf veins in a dicot spreading everywhere, not parallel. If we look at vascular bundles in a monocot, vascular bundles are scattered, while in dicot they are arranged in a ring, as you can see here. Vascular bundle consists of the xylem and the phloem and all the conducting tissues of a plant. So they occur in bundles, while in dicot they occur in a ring. And floral pattern also shows some differences. Floral parts in multiples of 3, while floral parts in multiplexes of 4 or 5. So this is a general observation of floral patterns. So again, to emphasize, monocot and dicot, the basic difference is number of cotyledons during the germination phase of the crop. So lettuce is a dicot crop, while all the rice grains and everything, these are monocot crops. Yeah, is it clear to the students? You can just mention yes or no in the chat. So we learned about a monocot and a dicot. We saw some examples, some characteristic differences. It's okay if you couldn't answer this. This was just a memory based question. Lettuce is a dicot. That was the answer to this question. Is it clear to the students? Yes, yes, yes. Cool, cool, cool. Nice. Let's move on to the next question. Question number 6. Which of these is an inorganic antioxidant? Which of these is an inorganic antioxidant? Option A, anthocyanin. Option B, cerium oxide. Option C, superoxide dismutase, or option D, glutathione? I hope you can see my screens. Which of these do you think is an inorganic antioxidant? Anthocyanin, is it cerium oxide, is it superoxide dismutase, or glutathione? You must have read about antioxidants. The whole lecture 5 must have some details about antioxidants, right? So you might be able to answer this question. It's okay, take your time, students, and try to answer this. I'll wait for a minute or a couple of minutes and then collect some answers. Inorganic antioxidant. Okay, I see some answers. Abhinav is saying B. Aditi, Roshan, Gaurav are all going with B, serum oxide. Komal is saying glutathione. Anuradha is saying serum oxide. Okay, let us see what is the correct answer. The correct answer is B, serum oxide. Well done. Most of the students have answered B correctly. So if you see, it's pretty straightforward. If you see all these options, which of these is an inorganic antioxidant? Forget about antioxidant. You just filter out, if you're clever enough, just filter out the inorganic compound in all these, and the first hit that you get is the answer, is cerium oxide. Anthocyanin, cyanin, superoxide dismutase, glutathione, all these are biological pigments or enzymes or proteins, all kinds. But cerium oxide is an inorganic molecule consisting of cerium as a metal, oxides of cerium. So we also have cerium oxide nanoparticles. So cerium oxide is the correct answer. It's an inorganic antioxidant. Cerium oxide nanoparticles, or short form known as CENPS, have been shown to exhibit antioxidant capabilities, especially in scavenging reactive oxygen species. So the major areas CNPs have been used is to scavenge the reactive oxygen species in any plant or a crop. Because we know reactive oxygen species are often very harmful or create damage, we can use these nanoparticles. And what is the characteristic that makes CNPs as a good antioxidant? It is also mentioned by Professor Mainak Das in his lectures. The ability of CNPs in switching the oxidation state of C3 plus and C4 plus makes it a good candidate to mediate reactive oxygen species. So in a cerium oxide molecule, the oxidation state of cerium can change from 3 plus to 4 plus. This makes it a good candidate for mediating reactive oxygen species because it can accept an oxygen and increase its oxidation number from 3 to 4. Thereby, it can sequester the reactive oxygen species or a free radical of the oxygen. That's why CNPs are so successful as an antioxidant. Direct scavenging of OH radical. So this is an OH radical, nitric oxide radical, and nitrate by CNPs have been investigated. So there are multiple reports where CNPs have been used for scavenging of OH radicals, nitric oxide and nitrate radicals. Moreover, previous studies indicated that CNPs have catalase and superoxide dismutase like effect. So catalase and superoxide dismutase are two enzymes, two proteins and enzymes which are present in biological cells, which are the inherent mechanism of the cells to deal with reactive oxygen species generation. So CENPs, cerium oxide, have shown activity at par with the biological catalase and superoxide dismutase. Both effects are closely correlated with the Ce3 plus and Ce4 plus surface concentration, pH, H2O2 and chelating ligand concentration. So this statement just tells us the property of cerium to change its oxidation state is a major factor leading to its antioxidant property. Here is a representation of a CNP or cerium oxide nanoparticle showing many kind of reaction it catalyzes. So if you focus on two or three reactions, a catalase like reaction in which H2O2 is converted into H2O plus O2. So H2O2 is a peroxide, hydrogen peroxide. It is a reactive oxygen species. In presence of CENPs, it is converted to water and harmless oxygen. Direct scavenging of OH radicals, here it is shown in number 1, and superoxide dismutase like reaction in which O2 radical, this is superoxide radical, is converted into H2O2, lesser reactive form, and then this H2O2 can be again used here in a catalase like reaction to form H2 and O2, thereby discharging the effect of reactive superoxide radical, which is carried out by superoxide dismutase enzyme. So CENPs have been able to show catalase like activity and SOD like activity. That's why it is a very useful nanoparticle which can be used as an antioxidant in many cases. That's about CENP. Now what are anthocyanins? Anthocyanins are a group of antioxidants found in red, purple and blue fruits and vegetables. So there are many peculiarly colored fruits and vegetables. So anthocyanins are those colored pigments found in the fruits and vegetables, mostly in berries. So if you have had blueberries, raspberry, cranberries, all these berries have lots of anthocyanins which impart the characteristic color of the berry. They belong to the flavonoid family. So these anthocyanins are part of flavonoids. Flavonoids are a part of larger group of antioxidants known as polyphenols, which are believed to help prevent or treat health conditions connected to inflammation and oxidative stress. So flavonoids have long been discovered as antioxidants. They consist of characteristic groups called for polyphenols. They are polymers of phenolic groups and they are good antioxidants. So if you see here the facts that I was mentioning, you must have heard that pomegranates are a good source of antioxidants. So pomegranates contain these colored pigments, flavonoids, which also contain anthocyanins. This is the structure of anthocyanins. So you can see here these benzene rings with OH are phenols and these are compounds of polyphenols where many phenolic groups are connected together with additional functional groups, and these have antioxidant capacity. They are used as primary antioxidants. They scavenge the radical production. So if there is a oxygen radical, reactive oxygen species, oxygen radical, peroxide radical, or a superoxide radical, these anthocyanins will sequester it with its functional groups, and they are also used as metal chelators or secondary antioxidants. Now the third option that we had was glutathione. What is glutathione? Glutathione is an antioxidant in plants, animals, fungi, and some bacteria and archaea. So this is an antioxidant found across the living phyla, found in plants, found in animals, fungus, even some bacteria and archaea have this. Glutathione is capable of preventing damage to important cellular components caused by sources such as ROS, reactive oxygen species, free radicals, peroxide, lipid peroxides, and heavy metals. So the role of glutathione has always been to prevent damage to cellular components. And these are some of the a summary representation showing the roles of glutathione. It is a powerful antioxidant. It also supports immune function, improves skin elasticity, reduces oxidative stress, supports overall health, and detoxifies and protects the liver. So glutathione is many a times supplied as a supplement or a medicine to naturally supplement the body's functioning because it has such health beneficial roles. So this is the difference between anthocyanins, glutathione, and cerium oxide, and the other one was what was the other one? Yeah, superoxide dismutase. So anthocyanin, superoxide dismutase, glutathione are all organic biological antioxidants, while cerium oxide nanoparticle is an inorganic antioxidant. And we learned about many of these species: anthocyanin species, cerium nanoparticles, glutathione. Is it clear to the students? Please let me know in the chat. I hope it's easier to understand this way, and that's why I spent time on behind the rationale of the answer so that you revise and brush through topics while going through this practice problem session. Is it clear to the students? Yes. Yes, nice. Cool. Let's move on to the next question. Okay, question number 7. Chitosan and triclosan are used for dashed. Two chemicals or two molecules, chitosan and triclosan, are used for dashed. For elemental analysis, as a biocide, as imaging tools, or as lipids. It's a tricky question. Chitosan and triclosan. What do you think they are used as? Try to recall and you will be able to answer. I'll encourage all the students to participate in this discussion and mention your answer in the chat box. Whatever you think is the right answer. You can also guess, just the effort is necessary. Doesn't matter if your answer is right or wrong. We will eventually lead to the right answer and see the explanation and rationale behind the right answer. So please take your time and try to answer. We are almost reaching to the last few questions. So you can also clearly see the question on the presentation. Chitosan and triclosan. What do you think is the correct answer? You can mention in the chat box. I'll wait for a minute or two and collect some answers. Then we'll proceed. And students who are already answering and going on with me, very good. Keep up the good work. You should also not stop answering and try to answer everything. I can see some answers. Okay. Abhinav says B as biocide. Preeti Singh 4. Janish, Gaurav, Roshan, Pritika, Umar, oh most people, Ganeshan, Anuradha, Abhirami, Shurbi, Aditi are all saying B, but some people also answered as lipids. Let's move on to see what is the correct answer. B is the correct answer. Well done. You guys have all answered very correctly. Chitosan and triclosan are used as biocide. Now, what is a biocide? A biocide is something which kills microorganisms or kills any form of unwanted living organisms, right? So if you are trying to kill something, that side, and bio is for living. So we have pesticides, we have herbicides. So all these are killing. All these are a form of biocide. Pesticide is very specific. It will kill pests. Herbicide will kill herbs and so on, right? So biocides are agents which can kill living organisms, not big humans, but as per se. Chitosan and triclosan are biocides. Now chitosan and its derivatives can be called environmental purification functional materials, as they can effectively control growth and reproduction of hazardous bacteria and also control toxic pollutants. This is what I meant when I was speaking of chitosan as a biocide. It can prevent the growth and reproduction of hazardous bacteria. It can kill hazardous bacteria which we do not want in our waters, in our sewage, in our soil, and anywhere. And it can safely be called as an environmental purification functional material. This is a schematic showing mechanism of action for chitosan. If you follow my cursor, here this shows a cell membrane and cell wall of a bacteria, of an hazardous bacteria. So there are many molecules if you look at in cell wall and cell membrane of a bacteria. Cell wall consists of manoproteins or mannose sugars, beta glucans, chitin. So there can be many kinds of polymers and proteins in the cell wall of a bacteria or an archaea, and there is this cell membrane. And these black gray molecules are chitosan molecules. So first, the chitosan interacts with the phospholipids of the cell membrane. The cell membrane, chitosan will break the cell wall, go inside, interact with the phospholipids of the cell membrane, and then destroy the membrane. Number two step, part two, is destruction of the membrane, which is leading to the cell death. So this is the mechanism of action of chitosan. It can dissolve or destroy the plasma membrane or puncture holes into the plasma membrane of bacteria. Now that the bacteria has all its plasma membrane punctured little holes, so the osmolarity between the outer surrounding and the inner environment of the bacteria will change, and there will be exosmosis and plasmolysis which will kill the bacteria, because the primary function of the membrane is to maintain the osmolarity, the pH, and to prevent outer environment to influence the inner environment. So puncturing holes into the membrane through chitosan will lead to the death of the bacteria. The most prevalent proposed antibacterial activity of chitosan is by binding to the negatively charged bacterial cell wall, causing disruption of the cell, thus altering the membrane permeability. See, this is what I was talking about. The membrane becomes permeable. Earlier it was impermeable, means not many substances can pass through. Only substances can pass through into the cell via channel proteins or carrier proteins or aquaporins or stuff like that. So now we have introduced a molecule which can puncture holes into the cell membrane, compromising its membrane permeability, followed by attachment to DNA causing inhibition of DNA replication and subsequently cell death. So one of the proposed mechanism, is that chitosan goes inside. First, it punctures the cell wall, cell membrane, goes inside the cell, binds to the DNA molecule, and inhibits the DNA replication, leading to cell death of the bacteria. Right? Now, what is triclosan? Triclosan is also an antimicrobial agent that has been used long back, more than 40 years, as an antiseptic, disinfectant, or preservative in clinical settings. So, in clinical settings and in hospitals, triclosan laden water is used as antiseptic and disinfectant to mop the floors and to sterilize the patient surroundings and everything. In various consumer products, including cosmetics, plastic materials, toys. So, triclosan is also used in all these consumer products so that people touching these products, children playing with toys, plastic materials, do not get any chance of microbial infection because triclosan is the product itself has antimicrobial property. Triclosan has a broad range of activity that encompasses many but not all types of gram-positive, gram-negative, non-sporulating bacteria, some fungi, Plasmodium falciparum and Toxoplasma gondii. Although triclosan has a broad range of activity, it means it can act on variety of harmful microbes. Still, it cannot act on all of them. Many important types are left out, such as some types of gram-positive and gram-negative bacteria, some fungi, Plasmodium falciparum, which causes malaria, and Toxoplasma gondii. Toxoplasma gondii is also a dreadful pathogen. Triclosan has not been able to neutralize all these pathogens, but it has in a general broad range of activity where it can be used as an antimicrobial agent for various consumer products and hospital settings. So this is the structure of triclosan: two benzene rings, chlorinated benzenes with grouped with an attached with an ether linkage to another OH and Cl laden benzene ring. So this is the structure of triclosan. Triclosan is bacteriostatic at low concentrations, but how higher levels are bactericidal. So it's such convenient to use triclosan because at lower levels it is bacteriostatic. By bacteriostatic I mean it can stop the growth of bacteria, or it can bring the bacteria to static phase where the bacteria cannot grow. But at higher concentrations, triclosan is bactericidal. Cidal means killing, suicidal, self-killing. So triclosan can act as bactericidal in higher concentration. It can kill the bacteria, and in lower concentrations, it can stop the growth of bacteria. So upon our convenience, we can use triclosan both as a bacteriostatic material and a bactericidal material. At sub-lethal concentrations, lethal means death concentration which can kill the microbe. So below that, at sublethal concentration, it acts by inhibiting the activity of bacterial enoyl acyl carrier protein reductase, which is Fab1, a critical enzyme in bacterial fatty acid biosynthesis. So whenever it is used in low concentration, it impairs the enzyme and affects fatty acid synthesis of the bacteria. That's why bacteria growth is affected. At bactericidal concentration, means at higher concentration, it is suggested to act through multiple non-specific mechanisms including membrane damage. So at higher concentration, which is killing the bacteria, it also follows the same pathway such as chitosan. It damages the membrane of the bacteria and then causes DNA damage and change in osmolarity and pH balance of the bacteria. So in these ways, chitosan and triclosan both act as bactericidal agents or as a biocide in agriculture and in other industries. So students, is it clear? Is it clear to you guys? Is it easy to understand? You can just let me know in the chat box. We learnt about triclosan and chitosan as a biocide used in various productions and crops as biocidal agents, killing harmful bacteria. Some damages the cell membrane, some can be concentration dependent, stop the growth of bacteria. Yes, yes. Cool, cool. Moving on to the eighth question. Which of the following is most commonly used MRI contrast agent? I'll repeat the question. Which of the following is the most commonly used MRI contrast agent? Option A, gunmetal. Option B, zinc. Option C, oganesson. Option D, gadolinium. Which one do you think is the correct answer to this question? Which one of these is an commonly used MRI contrast agent? Is it gunmetal, zinc, oganesson, or gadolinium? Mention your answer in the chat box. I'll encourage students all to participate. We have two more questions left to end this sessions. We are already at 4:30 now. People who haven't gotten a chance to answer, please come up. Be confident and put your answer in the chat box. It's okay if it's wrong. I'll wait for a few minutes and to collect some answers. After a minute, we can discuss the answer. Which of the following is the most commonly used MRI contrast agent? Everybody is encouraged to answer. Try to type out the answer in the chat box. I see some answers already. Yeah, many have answered. Abhinav is saying D. Surbi says A. Abhinami says option 2, zinc. Aditi, Anjali, Roshan, Komal, Anuradha, Janish are all going with option D or 4. Some people have answered gunmetal, zinc. Majority are answering gadolinium. Let's see what is the correct answer. Great. Option 4, gadolinium, or option D, gadolinium is the correct answer. Well done to all the students who have answered option 4. Gadolinium is the most commonly used MRI contrast agent. Right? So what actually happens in an MRI machine? And where do we need gadolinium? What happens in MRI scanners is many sections of our body, whatever thing or whatever organ or whatever region needs to be MRI scanned, that is exposed to a strong magnetic field. So MRI stands for magnetic resonance imaging. So what we do is we subject the area to be imaged with strong magnetic field, causing primarily the hydrogen nuclei of water in tissues to be polarized in the direction of magnetic field. So what it does, it all our tissues contain water. In the water molecule, the hydrogen nuclei will get polarized due to presence of strong magnetic field in the direction of magnetic field. Nextly, an intense radio frequency pulse is applied that tips the magnetization generated by the hydrogen nuclei in the direction of receiver coil where the spin polarization can be detected. Then what happens? Then a frequency pulse is supplied which will turn the polarization of hydrogen to the receiver coil where the spin polarization can be detected. How much the hydrogen nuclei have polarized in the direction of magnetic field. Random molecular rotational oscillations matching the resonance frequency of nuclear spin provides relaxation mechanisms that bring the net magnetization back to its equilibrium position in alignment with applied magnetic field. So now that we have excited the hydrogen nuclei to spin towards the magnetic field in response to the strong magnetic field, we will then allow it to relax back to its equilibrium with random molecular rotational oscillations. And the magnitude of spin polarization, which is measured by the receiver coil, detected by the receiver, is used to form the MR image, but decays with a characteristic time constant known as T1 relaxation time. So whatever this polarization of hydrogen nuclei is captured by the receiver, this is used to form the MRI image. But this spin polarization or the polarization decays with time called T1 relaxation time. Water protons in different tissues have different T1 values. So this is the characteristic value of an MRI imaging. Each tissue can have different T1 values, which is one of the main sources of contrast in MR images. So that's how contrast is produced in MRI images. High T1 values of one tissue and low T1 values of the adjoining tissue will produce a contrastive image. Now here comes the role of a contrast agent. A contrast agent usually shortens, but in some instances increases the value of T1 of nearby water protons, thereby altering the contrast in the image. So what will the contrast agent do? It will reduce the T1 relaxation time between different tissues so that the contrast can be changed or altered on our will and therefore produced a high resolution MRI image or a scan. And this is how an MRI image looks like. So the contrast, you can see black and white contrast, grayish borders. So there are different colors in form of contrast of black and white. So this contrast can be increased or decreased depending on the use of a contrast agent in MRI scanning. So if you summarize, in MRI scanner we provide magnetic field. Water is present in all tissues. Water will have two hydrogen nuclei which will get polarized in the magnetic field. This polarization is then received by a receiver, and then this polarization decays with the time via relaxation, which is known as T1 relaxation time. Now a contrast agent can increase or decrease this T1 relaxation time. That's where its use comes as in an MRI scanner, right? Now gadolinium is a chemical element with the symbol Gd and atomic number 64. Gadolinium is a silvery white metal. When oxidation is removed, it is only slightly malleable and is a ductile rare earth element. So gadolinium is a rare earth element. Rare earth element starts with lanthanum, atomic number 57. So gadolinium is atomic number 64. The silvery white metal looks like this. Gadolinium reacts with atmospheric oxygen or moisture slowly to form a black coating. So if you isolate the mineral, the metal, it is a silvery white metal, but in exposure to air, it reacts with oxygen to form a black coat. Now, traditionally, gadolinium based contrast agents are untargeted, generally distributing throughout the body after injection, but will not cross the intact blood brain barrier. Brain tumors and other disorders that degrade in the blood brain barrier allow these agents to penetrate into the brain and facilitate their detection by contrast enhanced MRI. So, gadolinium based contrast agents are readily used to detect brain tumors and other brain disorders because of the blood brain barrier, which does not allow which does not allow many molecules present in the blood to cross into the brain. So this gadolinium will not cross the blood brain barrier, but brain tumors and other disorders that degrade the blood brain barrier. So when there is a tumor in the brain, it will destroy the blood brain barrier and thus will allow the gadolinium to penetrate into the tumor, into the brain or in wherever, and allow the imaging. So only when a patient will have a brain tumor, only then can gadolinium enter into the blood brain barrier and produce a contrast image of the MRI, thus allowing easy detection of brain tumors. Because because of this, gadolinium is used as a traditional contrast agent in MRI scan imaging. Is it clear to the students? We learnt about what is the principle of working of MRI scanner and how gadolinium is used. What is the atomic number of gadolinium? How does it look like? Is it clear to the students? The answer will be gadolinium is a contrast agent used in MRI image scanning. Just let me know in the chat box. Yes. Roshan is saying yes. Rohita, Anuradha, yes. See, students, I keep asking for your confirmation because if you're not able to follow anything, I can repeat it for you and we can go back in the slides and understand it better. But once you get through it, I want all these concepts to be drilled into your head so that when you face the main exam or when you complete this course, this doesn't go out of your head. The basic principles, these are very easy. I'm just mentioning it. I'm collecting the information and providing it to you. So you please be honest and let me know if you're able to understand or not. Cool. Let's move on to the next question. Question number 9. Lectins are dashed. Proteins that bind to proteins. Proteins that bind to carbohydrates. Carbohydrates that bind to carbohydrates. Carbohydrates that bind to proteins. Which one do you think is the correct answer? What are lectins basically? Are they proteins that bind to proteins? Proteins binding carbohydrates, carbohydrates binding carbohydrates, or carbohydrates binding proteins? Just type your option in the chat box. I'll wait for a minute. After this, we have one more last question before we end this session. So I'll encourage all the participants who haven't gotten a chance yet to answer the question. Please come forward and mention your answers in the chat box. Be confident enough. We'll discuss the correct answer and find the rationale behind the correct answer. Right? Don't shy out and even if you haven't gotten a chance to answer all the 10 questions, you can just try out these last two questions. I'll wait for a minute more. There are some answers coming up. What are lectins basically? Okay, seems like there are many answers. Anuradha says B, Aditi 2, Surbi, Abhirami, Anjali, Komal, Amarjeet, Roshan. Roshan changed to option 4, and Janish. Mostly people are answering option 2. Let's see what is the correct answer. Option 2 or option B, proteins that bind to carbohydrates, is the correct answer. Lectins are proteins that bind to carbohydrates. I'm sorry, Roshan, but your previous answer was correct. Carbohydrates that bind to proteins are called glycoproteins. Or you can say there are proteoglycans, and there are glycoproteins, there are less lectins. So these are all little confusing terms. We will learn about what lectins are so that it can clear out your doubt. Anyways, most of the people have answered correctly. Lectins are the proteins that bind to carbohydrates. Yeah. Lectins are defined as proteins that bind to carbohydrates. Lectins have a role in recognition at the cellular and molecular level and play numerous roles in biological recognition phenomena involving cells, carbohydrates, and proteins. So, lectins act as molecule of recognition for many living cells and for many membranes, many cell walls. So, recognition part is played by lectins. Lectins are proteins that can bind carbohydrates. While there are two other terminologies, proteoglycans and glycoproteins. Glycoproteins are majorly proteins that have glycomodification. Glyco means sugar modifications. So glycoproteins are majorly proteins which have sugar modifications. Proteins are made up of amino acids, and if these 3D structural proteins have certain sugar modifications like attachment of sucrose or mannose or any other polysaccharide or a monosaccharide to the protein, then that protein is called a glycoprotein. The base is protein. While proteoglycan, the base is polymer or a sugar polymer. Glycan is the base. So to a polymer, there is a molecular protein attached, or to different sugar molecule is the base presence in abundance, and to that few amount of proteins are attached. So these are proteoglycans. The base molecule is glycan. Glycoproteins, while on the other hand, ex- sorry, I couldn't. Can you mention your question in the chat, please? I missed it. I think it's Roshan. Yeah, you can post your question in the chat. So what we were talking about is those similar kind of terms, confusing terms. So lectins are definitely proteins. Lectins are base proteins which can bind to carbohydrates. They have binding sites for carbohydrates. Those are lectins. Roshan is asking if the answer is 4. I think the answer should be proteins that are binding to carbohydrates. Lectins are proteins that bind carbohydrates. I think B is the correct answer. That's what I know. That's what was mentioned also. So lectins are definitely protein, Roshan. I would like to stand with my answer. Lectins aren't carbohydrates to begin with. They are basically proteins that can bind to carbohydrates. Carbohydrates that can bind to protein are called proteoglycans. Or they have proteoglycans are those carbohydrates which are in conjugation with protein already. So, so proteoglycans are like proteins that are heavily glycosylated. Lots of glycosylated means there are lots of sugars on these protein molecules. While carbohydrates that bind to proteins, you are asking about, uh, you are asking about option 4, carbohydrate binding proteins. So if you carefully, so there is a trick to this option. If you carefully see, understand the question, option 4, lectins are proteins that can bind to carbohydrate. So the confusing part is protein and carbohydrate interaction. Protein and carbohydrate interaction is happening in lectin, but lectin is a protein. Lectin is not a carbohydrate. That's why we have this. So here in option 4, we have option 4. If we go by the terminology, lectins are carbohydrates that bind to proteins, which is not true. Lectins are proteins that can bind carbohydrates. So that is the definition that was what I was coming into. Lectins are defined as proteins that can bind to carbohydrate. So you are right. There is a protein and carbohydrate interaction, but lectins are proteins. If you study, so any molecule generally with I ends refer to proteins. So where you have ferritin, you have ferritin is a protein. Lecithin, as we discussed, a group of emulsifying fat and agents. But here, lectins are proteins. Lectin is a protein which can bind to carbohydrate. So please bear with me. This is the correct answer. I thought you might be confused. Lectins also mediate attachment and binding of bacteria, viruses, and fungi to other intended targets. So lectins also act as attachment molecules. So uh, more detrimental effects of the lectin, because presence of lectin can attract bacteria, viruses, and fungi. Yeah, no issues, Roshan, and Komal has also helped me in answering this question. Lectins are basically proteins. Yeah, good that you had your doubt cleared. So here is the representation showing the presence of examples of different lectins. Langerhans cells, these are cells present in the pancreas, islet of Langerhans, you must have heard. These are the center for diabetes. If these cells go bad, then you have diabetes, you have pancreatic cancer and everything. So presence of these lectins, lectin 2, langerin, this can attract pathogens like S. aureus, Staphylococcus aureus, Staphylococcus pyogenes. These are all bacteria which are pathogenic. Dectin, MGL, DC sign, these are present on dendritic cells. They can also attract a range of bacteria, viruses. Helicobacter pylori, this is a major causative of gastric cancer. Why pseudotuberculosis? This is also a pathogenic bacteria. E. coli, S. aureus. These are S. aureus is Staphylococcus aureus again. E. coli, Escherichia coli, Neisseria gonorrhea. So these are all Clostridium jejuni. These are all pathogens which can recognize these lectins present on cell surface. And also, similarly, we have some lectins on monocyte macrophage boundary also. Lectins, as I mentioned, are one of the many toxic constituents of many raw plants that are inactivated by proper processing and preparation. So there is a scientific reason why we should cook our food properly before consuming, because many of the plant cells contain lectins which are toxic to our body. So that's why cooked and processed food is always harmless and healthier while eating. So we just not don't cook food for taste. We also cook because cooking food is a healthy process of deactivating all these lectins which can be toxic constituent. For example, here's an example: raw kidney beans or rajma beans, basically what we eat in North India. naturally contain toxic levels of lectin. So these lectins are very notorious for their activity of agglutination. They will form aggregates and form a blockage. Adverse effect may include nutritional deficiencies and immune reactions. So if you do not cook raw kidney beans very properly, then you can have agglutination defects because of presence of lectins. So here is a schematic again summarizing what are lectins. Lectins are naturally occurring proteins that can bind to carbohydrates. A wide variety of plants and animals contain them. Lectins defend plants from predators through antibacterial, antiviral and others activity. Are lectins good for us? Lectins have various functions involving cell signaling and inflammation. Some have been shown to induce inflammation while others are anti-inflammatory. So sometimes lectins can induce inflammation, sometimes not. There is still much we do not know about role of lectins in health. Peanuts have lectin, and does cooking eliminate lectins? Yes. Raw peanuts contain higher amount of lectins. Studies have shown that 98 to 100% of lectins in peanuts are destroyed after boiling, microwaving or roasting. So any food which contains toxic lectins or which can serve as entry point of viruses and bacteria, as we saw in the earlier slide, we can deactivate them via proper heat cooking and fermentation. Is it clear to understand? Lectins are basically proteins that can bind to carbohydrates. I hope it is clear. Thanks for asking your doubt to get it clear. You can just type in the chat box if it is clear for you guys. Then we'll move on to the last question of this session. Yes, great, great, great. Cool. So, last and final question of this session. Which of the following nanoparticles reduced germination percentage in spinach and radish? So this is a direct, easy question from the lecture series. If you have been through the lecture series thoroughly, Professor Mainak has taken a whole good amount of time explaining the experiment involving spinach and radish and activities of different nanoparticles. Which of the following nanoparticles reduced the germination percentage in spinach and radish? Is it option A, zinc, option B, silver, option C, CEO2, cerium oxide, or option D, magnesium? Which of these nanoparticles? Is it silver nanoparticles, zinc nanoparticles, magnesium nanoparticles, or cerium oxide nanoparticles? This is the last question, students. So anybody who wants to answer or who hasn't gotten a chance to answer in the previous questions, just try to answer this. Type, all you have to do is type your comment or type your option in the comment box. Not much of a big deal. You can see the question on the slide, think about the answer. Even if you do not know it, cannot recollect it properly, you can just guess. It's okay if the answer is wrong, we will understand the rationale behind the correct answer, right? So I'll give a minute to all of you guys, try and find out the answer in the chat box. Which of these do you think is the correct answer? I'll wait for a minute and collect some answers. There are already some answers. It's good to see people are so enthusiastic and interactive. Makes the class much more fun, this problem solving session. We'll wait for a minute for others to answer and then we'll wind up with this explanation, our session. I can already see some answers. Aditi's Aditi, Roshan, Janish are saying 3. CO2. Komal, Anuradha and Rohita says silver. Nandlal says zinc. And Anish Kumar is saying CO2. Okay. So there are certain zinc people, some people answering silver and others going for cerium oxide. Poor magnesium, nobody is going for magnesium. It's fine. Let's see what is the correct answer. Correct answer is option C, cerium oxide. Congratulations to all the students who answered C. They are right. Now let's understand what happened with germination. Germination is promoted by removal of blockage offered by antioxidant enzymes. This is the exact statement that uh, Professor Mainak Das mentioned in one of his lectures, where I think, week 5, lecture number 3, where he was mentioning use of nanoparticles, use of other nanoparticles other than iron pyrite. Germination is promoted by the removal of blockage offered by antioxidant enzymes. So, in a germinating seed or a cotyledon, antioxidant enzymes are the ones which provide a block so that the seed cannot germinate. Amylase is an enzyme which breaks down starch and provides plant with energy to start germination. So, in contrast to this, amylase is an enzyme which will break down the starch present in the cotyledon and then provide the plant with the energy to start germination. So, what do these antioxidant enzymes do? They prevent the activity of amylase, which will delay the germination. Because activity of amylase will provide energy to the plant and then the plant will start germination. So, what do these antioxidant enzymes do? They prevent the activity of amylase. Now, cerium oxide nanoparticles have antioxidant property. This is the one that we encountered in question number 6 or 5, I guess, where we used cerium oxide nanoparticles for their antioxidant property, where it can sequester reactive oxygen species, act like catalase and superoxide dismutase. So CO2 nanoparticles have antioxidant property, which in addition to naturally present catalase, superoxide dismutase, and other enzymes, deactivates amylase and slows down germination. So this is the whole process of CO2 nanoparticles. In addition to uh, naturally present antioxidant enzymes like catalase, superoxide dismutase, presence of CO2 nanoparticles will additionally slow down the germination, because these will prevent amylase enzyme, which will not break down starch into the plant with energy to start germination. So this is a schematic showing the process of germination. The seed is planted and then there is emergence of radicle, hypocotyl, seed coat falls off, the radicle forms the root, while the plume will form the shoot. There are cotyledons generating. This is the hypocotyl, epicotyl, and first true leaves. So this is the process of germination, seed germination. And I have prepared a schematic for easy understanding of CO2 nanoparticle. So in the natural case, we have antioxidant enzymes such as catalases, superoxide dismutase, glutathione peroxidase. These are natural enzymes present in the plant or in the seed, antioxidant enzymes. These inhibit amylases. Amylases break down the starch into energy. So in the presence of antioxidant enzyme, catalases, superoxide dismutase, glutathione peroxidase, amylases cannot function very nicely. Therefore, starch cannot be converted into energy. When these are not there or their activity is inhibited, amylases can convert starch into energy. Then this energy can be used for germination of the plant. Now what happens when we have CO2 nanoparticles in presence of all these enzymes? Now CO2 nanoparticles will cause more inhibition of amylase by these antioxidant enzymes, because CO2 will also offer its antioxidant property, and this antioxidant property will inhibit the amylases. Now that the amylases are inhibited, there will be a slow conversion of starch into energy. The breakdown of starch into energy by amylases will slow down. Since there is low energy, now the process of germination will also slow down. That's why application of CEO2 nanoparticles will decrease the speed of germination or will slow down the germination because of antioxidant property of CEO2 nanoparticles. Is it clear to the students through this schematic? I made this schematic so that it will be easier to understand for the students how CEO2 nanoparticles can add on to slowing down germination. Now, slowing down germination can be applied in many cases where we need preservation of the seed. So we can preserve these seeds treated with CO2 nanoparticles for a longer time without germination. Is it clear to the students? Uh, I would please request switch off your mic and your video chat. That was very indisciplinary. Please avoid such acts because all we are all here to learn through this interactive session, right? So both let's both of our sides put effort in maintaining the discipline. So is it clear to the students why CO2 nanoparticle application decreases the rate of germination? Yeah, yeah, cool. With that, we have come to an end. I'll stop my screen, stop presenting. Yeah, with that, we have come to end of practice problem set week 5. So what I'll do now is I'll just paste. This is the playlist link to the playlist where I have uploaded all the practice session videos till now. Practice session problem set 1 to problem set 5. You can go through these playlists in my YouTube channel. You must have also received a mail at the start of these practice sessions where they have mentioned the Google Drive where I'll be uploading these slides that I was sharing with you today. So I'll upload these slides. The recording of these sessions will be uploaded into this playlist. You can go through if you have missed or if you want to re-watch any of the sections. So the purpose of these assignments are to help you solving your own assignments, or it's a kind of revision of what level of understanding you have of the course. So my job is to help you with that. And for any technical issues regarding registration of exam and all, that part I'm not dealing with. You can directly mail the NPTEL people. So I am just a PhD scholar um, who is doing TA-ship, and in my goal is to help you understanding the subject better. Yeah. So again, I'll be pasting here the playlist link where I'll upload all the recorded videos, and I encourage all of you guys to take some time out on to attend this problem solving session, which will and keep it interactive. Try answering the questions. That's what we aim to, and we'll solve some exemplar questions from the same lecture set for the week that we are designating. So it was good talking to you. Let's meet on next Sunday solving problem set week 6, and be prepared. Have a happy Holi. Happy Holi to everyone. I'll end this call. You can watch these recordings. I'll end this call, and thank you for joining.